burn like a pro.
You know how you can stir salt or sugar into water and just watch it vanish? It looks like it's gone for good. But in chemistry, gone is almost never the real story. So today, let's explore exactly how scientists get those invisible solids back out of the water. So let's put ourselves in that situation. You've made a solution. The solid has completely disappeared. How in the world do you reverse that process? How do you get it back? Not just as a pile of gunk, but in its pure solid form. Well, right away, we come to a fork in the road. We have two main paths we can take. Path 1 is a direct, kind of intense method called evaporation. Path 2 is a more patient, delicate process called crystallization. And trust me, picking the right path makes all the difference.
So how do you choose? It all boils down to one super important question about the stuff you dissolved. Can it handle the heat? Is it heat stable, or is heat going to destroy it? That one simple property, well, it changes everything.
And this shows you exactly what's at stake. For something tough and heat stable, like regular table salt, you can just use brute force. You crank up the heat, boil off all the water, and you're left with perfect salt crystals. But if you try that same thing with something delicate, like sugar, you just get a burnt, black, useless mess. That burnt mess has a scientific name. It's called thermal decomposition. It's what happens when heat doesn't just get rid of the water, it actually starts breaking apart the molecules of the substance itself. It literally shatters them. And that's the big danger we have to avoid. So let's just break it down nice and simple. If your substance is heat stable, go ahead, heat it to dryness. But if it's not, if it decomposes with heat, you absolutely can't. You have to heat it gently and only until the solution is saturated. Totally different rules, totally different outcomes, all based on that one property. Okay, so since it's the trickier one, let's dive into that more careful method. Let's talk about the delicate art of crystallization. This is where real technique comes into play. The very first step here is to make what we call a saturated solution. We're going to heat the liquid, but not to boil it all away. We're just warming it up enough so that it's holding the absolute maximum amount of the solid it possibly can. It's like the solution is full to the brim, perfectly ready for crystals to start forming. Now, what happens next is so important. It's all about speed. If you let that saturated solution cool down slowly, over time the molecules have a chance to line up perfectly and form these big, beautiful, well-defined crystals. But if you rush it and cool it down fast, you'll just get a fine powder. Time, it turns out, is the secret ingredient here. All right, enough theory. Let's see this in action. We're heading into the lab to synthesize some copper 2 chloride, putting this exact crystallization method to the test. Okay, so the experiment starts. Step 1, we add way more copper 2 oxide powder to our acid than we actually need. Why do we overdo it? To make absolutely sure every last drop of that acid gets used up and neutralized. Then, step 2, we filter out all that leftover black powder, leaving us with this pure blue solution. That's the stuff we want. And here's where we use what we just learned. Step 3, we gently heat that blue liquid until it's saturated, setting the stage perfectly. And then, for step 4, we just walk away. We let it cool down all by itself, nice and slow. No rushing because we're going for those big, beautiful crystals. And finally, it's time to harvest. We filter the whole mix to separate our amazing new crystals from the liquid. Then we give them a quick rinse with some cold water to wash off any leftover gunk and gently pat them dry between some filter paper. And what we're left with is our final product. Pure, dry copper 2 chloride crystals. Success! So as we wrap this up, it becomes really clear, right? Evaporation and crystallization aren't just two ways of doing the same thing. They are two totally different tools for two different kinds of jobs. The brute force evaporation is for the tough guys, the heat-stable stuff, and careful crystallization is for the delicate molecules that need a gentler touch. Look, if you remember just one thing today, let it be this. Success in the lab all comes down to following one simple rule. Match your recovery method to the heat stability of your molecule. If you get that part right, you're pretty much guaranteed a good result. And that leaves me with one last thought for you. We've just seen how slow, careful cooling can build these perfect, beautiful structures in a lab beaker. So my question is, where else in nature do we see this exact same process at work? What other amazing things are built slowly and carefully through crystallization?